All right. So today, what we will be discussing is differentiation.
Okay.
Okay. Now,
Mm-hmm.
that differentiation by itself, it is just us trying to find the gradient of a function. Okay. So let's say that we have a function f of x equals 3x plus 2. Now, what would be the gradient of this function or this line or the graph of this function? Is this a linear line? A linear equation?
Yeah.
Okay. So what would be the gradient?
Don't I need the graph to like find the gradient?
When it's a line, it is mx plus c, right?
Yeah.
So from the equation, can I?
Oh, 3.
It's 3,
Yeah.
right? From the equation, we
Yeah.
can find the gradient in this case. Okay.
Yeah. Okay.
Now, if I have a function, let's say, let's keep it simple to x square. Okay. Now, for x square, is finding the gradient easy? What would be the graph of x square look like?
Would it just be like a diagonal line?
X square. Zara, isn't it like this?
Oh yeah, you.
Okay. For x square, it is this graph, right?
Mm-hmm.
So whenever we have a quadratic, like a term of x square, the highest term is x square, then the graph will look of this shape. It can be here, it can be here, it can be here, it can be here, it can be anywhere, but the shape would be the same. Whenever the highest term we have is x square, the highest power term. Okay.
Mm-hmm.
So this is the curve. Now it's a curve. Finding the gradient on of a curve is something that is like, how can I like find the gradient for a curve when it is ever changing, right? The slope of this curve is ever changing. Gradient is the
Yeah.
slope, right?
Yeah.
Gradient is slope, and the slope is ever changing. But if you look into it, the slope is changing, but the slope is changing. Is it changing randomly?
What do you mean by randomly?
Like, is it that at one point it is negative, at another point it's positive, then it goes to infinity, then it goes to 0? Is it changing like that, or is there a pattern that
No.
we can see?
Yeah, it's like slowly getting like straighter, the line, as you
This
go up.
line is slowly getting straighter, so the gradient is slowly getting increased, right? Now,
Mm-hmm.
the gradient m by definition is y2 minus y1 divided by x2 minus x1, right?
Yeah.
By definition, that is the gradient. Okay. Now, if by definition that is the gradient, then let's try to find the gradient for this curve. Okay. By definition, let's take our this point to be x1 and take this point to be our x2. It is a function, right? So
Mm-hmm.
this point right here will be f of x1, and this point right here will be f of x2, right?
Yeah.
Now, if I want to find a gradient at this point of a curve, what is something that we normally do?
Draw a tangent.
We draw a tangent. We
Mhm.
draw a tangent crossing through this point and measure the gradient for that tangent, right?
Yeah.
But that is a graphical method, and that method, if we like try to do it for a wide variety of functions, it would take a lot of time, right?
Mhm.
For a wide variety of numbers or points, it would take a lot of time. So let's try to make this tangent or generalize this whole process of making the tangent and getting the points of the tangent. All right. So
Okay.
we have this point, and let's just consider this point to be our second point. If I draw a straight line through these 2 points, it is this line, right?
Mhm.
X2 is in fact x1 plus d, right?
Yeah.
Okay. X2 is x1 plus d. So using all of this different process, okay, let's try to figure out how we can make this line more representative of the tangent at this point. Okay.
Okay.
What if I move this point like on a normal line, on a normal straight line, it doesn't matter which 2 point I take, right? To get the gradient,
Mhm.
I will get the same gradient. But on a curve, what if I move this point a little closer? Okay. If I make this
Mm.
point come here, then the straight line is like this, right?
Yeah.
Is this second straight line more representative of the tangent?
Yeah.
Right? The first one was way off. The second one is a little less off. If I take this point now, it would become even more closer to the tangent, right?
Yeah.
So what is happening here is, if I choose the second point to be closer to the x1, the gradient comes out to be the gradient of, like, it gets closer and closer to the gradient of the tangent, right?
Mhm.
So essentially what we are trying to do now is we are trying to find a gradient between one point and the point right next to it, right? Because that would give us a gradient that would be more closely resemblance, give a more closer resemblance to the gradient of the line of the tangent, right?
Okay.
Okay. So what happens now is, if our x1, the first point is x1, right?
Mhm.
While our x2, we have said that it is the first point plus the difference, the distance moved from one point to the next point, right? Okay.
Yeah.
So x2 is this. If x1 is this and x2 is this, then our y1 will be f of x1, right?
Mhm.
Our y2 will be f of x2, which will be f of x1 plus d, right? Okay.
Okay.
Now, the key concept here that we are going to use now is, we want this d to approach 0. We want this d to be as small as possible. So we want this d to approach 0, right?
Yeah. Okay.
Okay. So what we
Mhm.
do now is we will be using this formula right here. Okay. So the gradient of a line is y2 minus y1 over x2 minus x1. Okay. Same formula we will be using for the curve. So this will come out to be f of x1 plus d minus f of x1 whole divided by x2, which is x1 plus d, minus x1. All right.
Okay.
From here we get f of x1 plus d minus f of x1 whole divided by d, right?
Yeah. Okay.
Now here there was a key thing that we wanted here. We wanted to do here. That was we wanted the D to approach 0, right?
Mm-hmm.
This is represented by writing LIM D approaches 0. And it is pronounced limit D approaches 0. Okay.
Okay.
So how we write it down is we write this down before wherever we want the D to approach 0. So in this case, we will write down limit D approaches 0, and then inside the bracket, we will write down f of x1 plus D minus f of x whole divided by D. Now, what was our function f?
X squared.
It was x squared.
Yeah.
So limit D approaches 0, x1 plus D whole squared minus x1 squared all over D. Now, what happens is if I apply this right now, if I say that limit approach D approaches 0 and I make this D go to 0 and make this D go to 0 because we want it to reduce to 0, right?
Mm-hmm.
Whenever we apply the limit, what happens is these D's will be switched with 0. We will assume that D has now became 0. Okay. Now the problem with that would be, what if D approaches 0 right now? What do you think would happen?
And like it'll be like an error because it can't divide.
Because we cannot divide by 0. Exactly. Perfect. Okay. Because the denominator cannot be 0, so we cannot just make it 0 right now. We need to somehow eliminate this D for this to work. Okay. So what we will do now is we will expand the whole expression that is inside the bracket. So limit D approaches 0, x1 square plus 2dx1 plus D square minus x1 square all over D. All right.
Mm-hmm.
Now I can see that x1 squared and the negative x1 squared, they will be cancelled out, right?
Yeah.
Leaving me with limit D approaches 0, 2dx1 plus D square all over D. From here, can I take D common from the numerator?
Yeah.
I can, right?
Yeah.
So limit D approaches to 0, taking D common from the numerator, we get 2x1 plus D whole divided by D. Okay.
Mm-hmm.
This D and this D can cancel out now, right?
Yeah.
So now I can write limit D approaches 0 and 2x1 plus D limit. Once I apply limit D approaches 0, what I would be left with is 2x1, right? Okay.
Okay.
So M is equal to 2x1 because we were calculating M, right?
Yeah.
So the gradient at x1 is equal to 2x1.
Okay.
Now tell me, Can we find a gradient at any point on the whole curve now? Did I say what the value of our x1 was? I just said it's x1, right?
Yeah.
This x1 can be 4, it can be 5, it can be 8, it can be -6, right?
Mm-hmm.
I did not specify anything for x1, right? So
Yeah.
that means the gradient for this whole curve for this function is 2x. Okay.
Okay.
For any point, at any point, if we want the gradient of that point or the gradient at that point, then the gradient will be equal to 2x for that point. And here is the whole solution for that. How we know that this is true, right?
Yeah. Okay.
Okay. Now, there is one thing that you might think that here there is a policy here because we cannot divide by 0 or we cannot cancel 0 by 0 the way we have done here. Okay. Had d been equal to 0, we could not do this. But because we know that d is not equal to 0, it is approaching 0, right?
Yeah.
If d is approaching 0, then that means that the value of d is something. It's not nothing, right?
Yeah.
D can be, let's say, 0.00001 or even smaller value, a very small value, a value that is very close to 0 but not 0. And we can cancel that value out.
Okay.
Had I
Okay.
applied it here, I would not have been able to calculate it properly. So it's better to eliminate such values. And that is why we have eliminated such value. Okay.
Okay.
And so from here, what we get is to get the gradient of any curve, we can find the gradient by doing limit d approaches to 0 f of x plus d minus f of x whole divided by d. Now, how can I say that I can find the gradient using this? Notice up here, when I define the gradient, this is the basic definition for the gradient.
Yeah.
The change in y divided by change in x. Now, going further, this is change in y, and this will be the change in y for any function f, it does not have to be x square, right? It can be any function. Okay.
Okay. Okay.
I did not specify what the function f is. It's just a function. So it can be a linear function, a quadratic function, a cubic function, a quartic function. Okay. It can be any function. While the denominator, that is again, this is our x2 and this is our x1. Right?
Mm-hmm.
So again, that does not change. And when we simplify that, we get to this, right?
Yeah. Okay.
So the gradient of any function can be found using this whole process. Okay.
Okay.
So the gradient of any function is this. And as I defined at the very start, differentiation is essentially the gradient, finding the gradient for a curve at some specific point. So this, in fact, is called the first principle of differentiation. Okay.
Okay.
And it
When
is
I was like learning differentiation, we were doing like something different. We were like we had to subtract something with the coefficient and then like I don't remember, but it was something like
we will get to that. Okay. That is
okay.
like that is the next step of it. But this is the process behind the differentiation. Okay.
Okay.
We'll get to that. Okay. So this is called the first principle of differentiation, and we write it as dy over dx or f prime of x. All right.
Mm-hmm.
These are the notations for differentiation. This whole process is called the first principle of differentiation. All right.
Okay.
So yeah. Now moving forward, what you might have studied is, let's say that y is equals to x to the power of n, then dy over dx will be equal to n x to the power of n minus 1.
Yeah.
Okay.
Yeah.
This is something that you might have studied. So what I want you to do now is, right here, I did the differentiation for f of x equals x square, right?
Mm-hmm.
This is the whole process for f of x equals x square. What I want you to do now is do differentiation for f of x equals x cubed, okay, using this whole process that I have used. All right.
Okay.
Okay. And just ask me wherever you find it difficult, wherever you are having some difficulty. Okay. So here is the whole working, like the first few steps of the working. And you can copy the steps, it doesn't matter. Okay. Just like
Okay.
go through it and try to find the differentiation
The
or
gradient?
yeah, just differentiate or differentiate. So what you need to do is differentiate f of x equals x cubed. Okay.
Okay.